It's Petey the Probability Pirate talking to you about represented sample spaces. And you better watch this video or I'll have you walk the plank, yeah!
First vocabulary term would be an independent event. That would be an event where one choice does not affect any of the possibilities for another event. So down here, you can see examples of 3 independent events. The first one would be rolling dice. So if you roll a pair of dice, your first roll does not affect your next roll. It doesn't matter what number you roll the first time. If you roll a 12 that first time with your pair of dice, it's not going to mean that you can't roll a 12 the next time. Your first roll does not affect your next roll. That's why it's an independent event. Next, we have picking a name out of a hat and then replacing it. So imagine you have a hat with little sheets of paper that have names on them, and you choose one of the names out of that hat. If you then put that name back in the hat, you make it an independent event, because if someone were to choose after you, they have the exact same number of possibilities that you did when you chose the name out of the hat. So by replacing that name, by putting that name back in the hat, you've made it an independent event. Lastly, we have spinning the Wheel of Fortune. So if you're not familiar with the Wheel of Fortune, it's just a giant wheel with a bunch of different dollar values on it. And when you spin it, it's going to land on one of those given dollar values. Now, when you spin it the first time and it lands on a dollar value, that first spin doesn't affect your next spin. It's not going to make it so you have different choices the next spin. You still have the exact same number of possibilities you did the first spin. So because your first spin does not affect your second spin or any of the other ones after that, spinning the Wheel of Fortune would be considered an independent event. Next vocabulary term would be a dependent event. That would be an event where each choice is affected by the previous choice. So down here you can see we have 3 examples of dependent events. The first one would be choosing numbers for the Powerball. So if you're not familiar with how they choose numbers for the Powerball, there's a bunch of different ping pong balls that have numbers on them, and they're all bouncing around. And then when they're ready to choose the numbers, one ping pong ball gets sucked up, and whatever numbers on that ping pong ball has been chosen for the Powerball. That's one of the numbers they've chosen. Now that ping pong ball stays up. The number that is on that ping pong ball cannot be chosen as any of the other numbers in the Powerball. So your first choice then affects your next choice. You have one fewer ping pong ball to choose from, and that continues on as you select more and more numbers for the Powerball. That's why choosing numbers for the Powerball is considered a dependent event. Next, you have choosing members for a team. So let's imagine for a second there's 12 people who want to play a volleyball game, and 2 of the people are chosen as team captains. When the first team captain chooses someone to be on their team, that choice then affects the next team captain's choice, because they have one fewer person to choose from. They can't choose the person that was already chosen to be on the other team. So because that first choice affects the next person's choice, choosing members for a team would be considered a dependent event. Lastly, we have picking a number out of a hat and keeping it. So imagine there's a hat with a bunch of little sheets of paper in it that have different numbers on them, and you choose one of the sheets of paper out of the hat and you keep it. Because you keep it, that then affects anyone else who chooses a sheet of paper out of the hat. They have one fewer choice than you did. So because you kept that sheet of paper, that would be considered a dependent event.
Don't get stuck swabbing the decks, it's example time!
Now example 1 says determine if the following events are independent or dependent. So the first one is choosing a president, a secretary, and a treasurer for ASB. Well, typically in ASB, a person only has one role. They are president, they are secretary, or they are treasurer. They cannot be president and secretary. They cannot be president and treasurer. Meaning that if you have a student body that you're choosing from and you choose one person to be president, that then affects your choice for secretary and treasurer, because that person cannot also be the secretary and they cannot also be the treasurer. So because your first choice affects your second and third choice, that would be considered a dependent event if a person can only hold one office, like we said. Part B, choosing a color of a hat. So when you are choosing a color of a hat, you have the entire visible spectrum to choose from, and your choice of the color of the hat does not affect anything else, any subsequent choices of colors for a hat. So choosing the color of a hat would be considered an independent event.
What did the ocean say to the pirate? Nothing, it just waved! You try!
Okay, doing the same thing. So choosing the winner and loser on The Voice. So let's imagine that you have 2 people to choose from. One's going to be the winner, one's going to be the loser. Well, if you choose one to be the winner, that person cannot also be the loser. So your first choice of a winner affects your second choice for the loser. Therefore, choosing a winner and a loser on The Voice would be considered a dependent event. Part B says picking a card for a magician and putting it back in the deck. So if we are choosing a card but putting it back in the deck, our choice of a card will not affect the number of choices that the magician now has. So because our choice did not affect the magician's number of possibilities or choices, we can consider this an independent event. Lastly, electing a president and a runner-up. So if we have two people to choose from in an election, one is going to be the winner and one is going to be the runner-up, meaning that if we choose one person to be the winner, they cannot also be the runner-up. So your first choice for the winner is going to affect your next choice for the runner-up. Therefore, this would be considered a dependent event. Next, let's talk about the counting principle. So this says, suppose an event can occur in P different ways, and another event can occur in Q different ways. There are P times Q ways that both events can occur. So what does this mean? Well, let's take a look at an example down here. So this says how many different three-letter passwords can be formed using the letters X, Y, and Z, if each letter can be used more than once. So in this example, we are choosing three-letter passwords, and we have, for each spot, three different letters to choose from, X, Y, or Z. Now, each letter can be used more than once, meaning in our first spot, we can choose X, Y, or Z. We have three possible choices. In our next spot, we can choose, again, X, Y, or Z, because letters can be used more than once. In our last spot, we again choose either X, Y, or Z. So the counting principle says to get the total number of possible outcomes, or in this case, the total number of possible passwords, you're just going to multiply 3 times 3 times 3. And you end up getting that there are 27 possible three-letter passwords that can be formed using X, Y, and Z if each letter can be used more than once. Now, example 2 says how many different two-letter names can be formed using the entire alphabet if each letter can be used more than once. So because in this question, we are trying to find the total number of possible outcomes, or in this case, total number of possible two-letter names, we are again going to use the counting principle. So again, we have two-letter names that we are trying to choose, meaning we have two spots to fill, one for each letter. Now, in that first spot, we can choose any letter from the entire alphabet. So how many letters in the alphabet? That would be 26. So there are 26 different choices that we could choose for that first letter in the two-letter name. Now, what about the second letter? Well, it says if each letter can be used more than once, meaning your first choice will not affect your second choice. So this would be an independent event. So if I have 26 letters to choose from the first time, I also have 26 letters to choose from the next time, meaning to figure out the total number of possible two-letter names, all I have to do is just multiply 26 times 26 according to the counting principle, and I get that there are 676 possible two-letter names that can be formed using the entire alphabet if each letter can be used more than once.
Why does it take a pirate so long to learn the alphabet? 'Cause he could spend years at sea. Har! You try.
Okay, this says on an iPhone, you choose a four-number password. If the numbers are 0 through 9 and the numbers can be used more than once, find the total number of possible passwords. So because we are finding the total number of possible passwords or total number of possible outcomes, we are again going to use the counting principle. This time, it's a four-number password, so we have 4 spots to fill. In that first spot, how many different numbers are there to choose from? Well, we can choose 0 through 9. So that would be 10 different numbers we can choose for that first space. Now, what about the next space? Well, it says numbers can be used more than once, meaning your first choice will not affect your next choice, making this an independent event. So if I choose, let's say 9 to be my first number, I could still choose 9 to be my next number. So I have 10 different possible numbers I could still choose from to be my second number. And I have 10 different numbers that I could choose to be my third number. And I have 10 different numbers I could choose to be my fourth number. So to figure out the total number of possible four-number passwords, the counting principle says I just multiply 10 times 10 times 10 times 10. And I end up getting that there are 10,000 possible four-number passwords if the numbers you can choose from are 0 through 9, and those numbers can be chosen more than once. Now, example 3 says, how many different ways can 6 books be arranged on a shelf? Now, this question may seem a little different, but you're still trying to figure out the total number of possible outcomes, the total number of possible arrangements, meaning we are going to use the counting principle. So there are 6 different books we are arranging on a shelf, meaning there are 6 different spots to fill. In the first spot, how many different books can we choose from? Well, again, there are 6 books. So we have 6 different books we can fill that first spot with. But what about the second spot? Well, if I choose a book to be in that first spot, I can't then also choose that book to be in the second spot, meaning my first choice is affecting my next choice, making this a dependent event. So if I have 6 books to choose from for the first spot, I'm going to have 1 less book to choose for the next spot. So I only have 5 books to place in that second spot. And then if I have 1 book in this spot, 1 book in this spot, I only have 4 books left to choose for that third spot. And then I only have 3 books left to choose for that fourth spot, 2 books for the fifth spot, and then 1 book left for that last 6th spot. Now, the counting principle says to figure out the total number of possible outcomes, total number of possible arrangements on the shelf, all we have to do is multiply 6 times 5 times 4 times 3 times 2 times 1. And we end up getting that there are 720 possible ways that you can arrange 6 books on a shelf.
How much did the pirate pay for his piercings? About a buccaneer. Har, you try.
Okay, this time it says how many different numbers are between 1,000 and 9,999 if no digits can be the same number. Now, this may not seem like it, but this is again a counting principle problem. We are trying to figure out how many different 4-digit numbers are between 1,000 and 9,999 and no digits can be the same number. So, because it's a 4-digit number, we have 4 spots to fill. In that first spot, because this number has to be between 1,000 and 9,999, our first number can be 1, 2, 3, 4, 5, 6, 7, 8, or 9. It cannot be 0. If it was 0, then this number would not be between 1,000 and 9,999. So we have 9 different numbers that we can fill in that first spot. Now again, the numbers cannot repeat. So whatever we choose for that first number, that choice is going to affect our next choice, making this a dependent event. So I had 9 different numbers to choose from this time, meaning in my next spot, I should have 8 different numbers to choose from. Hold on though. In the first spot, we couldn't choose a 0, but in this spot, we could have a 0. So while we do have 1 less choice than we did here, we also gained a choice by being able to include 0. So that means that we still have 9 different numbers to choose from in this second spot. In our third spot, we again are choosing a number now from 0 to 9, but we can't choose either of the 2 numbers we chose to be in our first 2 spots, meaning we have 8 different numbers to select for our third spot. And then for our last spot, we again are choosing a number from 0 to 9, but we can't choose any of the numbers we chose in the previous 3 spots, so there are 7 numbers to choose from for that last spot. Now the counting principle says to figure out the total number of different numbers between 1,000 and 9,999 if no digits can be the same number, you just take 9 and multiply that to 9, and then multiply that to 8, and then multiply that to 7, and you get that there are 4,536 different numbers between 1,000 and 9,999 where no digits are the same number. Now example 4 says draw a tree diagram to illustrate the possible combinations of heads and tails if you flip a coin twice. So tree diagrams are actually pretty easy. For the first flip, we have 2 choices. We can either get heads or we can get tails. So that's what that's going to look like. Now we're not just flipping a coin once though, we're flipping it twice. So after our first flip, let's say we get heads. Then for our next flip after that, we can either get again heads or tails. Let's say in our first flip we got tails. After that in our second flip, we could get again heads or tails. So by counting the ends of these branches, we get the total number of possible outcomes. And there are 1, 2, 3, 4 possible outcomes here. And if you wanted to double check, all you have to do is just take the number of choices you had in your first flip, that would be 2, and then multiply that to the number of choices you have in your second flip, which is again 2, because you can get heads or tails your first flip, and you can get heads or tails after your second flip. Meaning that by the counting principle, if we multiply these together, there are 4 possible combinations. Now example 5 says draw a tree diagram to illustrate the possible number of choices Anthony can make when deciding to bag 3 groups of groceries with either paper or plastic. So again, tree diagram's pretty simple. Anthony has 3 groups of groceries to bag with either paper or plastic. So in that first group of groceries, he can either bag it with paper or plastic. Now let's say he bags the first group of groceries with paper. That second group of groceries he again can either bag with paper or plastic. If he were to bag that first group of groceries with plastic, he can again choose for the second group of groceries to be bagged with paper or plastic. Now let's say he chose the first group of groceries to be bagged with paper, and then the second group of groceries to be bagged with paper as well. Then the third group of groceries, he can again choose to bag with paper or plastic. If the first group of groceries was bagged with paper, and the second group of groceries was bagged with plastic, his third group of groceries, again he can choose to bag with either paper or plastic. Now let's say his first group of groceries was bagged with plastic. Now let's say the first group of groceries was bagged with plastic, and the second group of groceries was bagged with paper. The third group of groceries he can choose to bag with either paper or plastic again. And lastly, if he chose to bag the first group of groceries with plastic and the second group of groceries with plastic, the third group of groceries he can again choose to bag with either paper or plastic. So to get the total number of possible outcomes, total number of possible combinations, you just have to look at the ends of these branches. How many ends of our branches are there? There's 1, 2, 3, 4, 5, 6, 7, 8. So there would be 8 different ways that Anthony could bag those 3 groups of groceries with either paper or plastic. If you weren't sure about that though, you could still use the counting principle. Remember, there are 3 groups of groceries, and each group you could bag with paper or plastic, paper or plastic, paper or plastic. So you have 2 choices for each of those group of groceries. Meaning by the counting principle, all I have to do to figure out the total number of possible choices, total number of possible outcomes, I just multiply 2 times 2 times 2, and I get that there are 8 possible combinations.
Why couldn't the pirate play cards? 'Cause he was standing on the deck. Arr, you try.
Okay, this says you want to play a sport in the fall and in the spring. In the fall, you are deciding between football and cross country, while in the spring, you are deciding between baseball, track, and lacrosse. Draw a tree diagram to show all possible combinations. So we are again making a tree diagram, which is pretty easy. Your first branches are going to be the first event, which is going to be what sport do you choose to play in the fall? And you're choosing between football and cross country. So it's going to look something like this. Now, if you choose football to play in the fall, you can then choose between baseball, track, and lacrosse to play in the spring. Let's say you chose cross country in the fall though. You again can still choose between baseball, track, and lacrosse in the spring. Meaning, if we count the ends of these branches, that would be the total number of possible combinations. So there'd be 1, 2, 3, 4, 5, 6 different combinations to choose from. And if you didn't trust your tree diagram, you could still use the counting principle. Remember, in the fall, you had 2 different choices. You could choose between football and cross country. In the spring, however, you had 3 different choices. You're choosing between baseball, track, and lacrosse. So to find the total number of possible combinations, the counting principle just says multiply 2 times 3, and you get that there are 6 possible combinations.